All right. It's my great pleasure to welcome all of you to our Penner lecture series, Saul and Beverly Penner lecture series. It's the first lecture of this particular academic year. We're very happy that Saul has endowed this lecture series so that we have the privilege of inviting distinguished speakers. And to introduce our speaker for today, I'd like to call upon Jorge Cortez.
Thank you, Sultan. So it's my great pleasure to introduce today's speaker, Professor Vijay Kumar. He is a UPS Foundation professor at the University of Pennsylvania. He got his bachelor's degree at IIT Kanpur and at his Ph.D. at Ohio State in '87, and he has been a faculty member at the University of Pennsylvania ever since then. So Vijay has played a number of leadership roles at UPenn. He's been Deputy Dean for Research, Deputy Dean for Education. He's been chairman also of the Mechanical Engineering and Applied Mechanics Department. And he's also been director of the well-known GRASP lab. It was in that capacity where I got to meet him in 2000 when I was a PhD student. But he has also played other leadership roles beyond UPenn in the broadly defined community on robotics and automation, and more recently as assistant director for robotics and cyber-physical systems at the White House Office of Science and Technology Policy. So you might wonder, with all the recent funding on robotics and cyber-physical systems, that might have something to do with Vijay spending some time at the White House. I have here a long list of distinctions and awards, but maybe I will just highlight a few. So he is or has been a member of numerous editorial boards of prestigious journals in robotics. He is a fellow of the ASME and IEEE, and he recently became a member of the National Academy of Engineering, together with Professor Richard Murray, who was one of our last Penner lecturers. So we tend to select them well. And he's won a number of awards. Early in his research career, the National Science Foundation Presidential Young Investigator Award, or the Frothstein Award for Significant Accomplishments in Mechanics and Robotics. More recently, in 2012, he's won a string of awards, most notably ASME Mechanics and Robotics Award, IEEE Robotics and Automation Society Distinguished Service Award, and World Technology Network Award. He's won also a number of best paper awards at numerous conferences, and his students have also won or been finalists for best student paper awards. And I'm sure you've heard of Vijay. He's been prominently displayed in numerous websites and media outlets. And maybe you've seen his TED Talk in the TED Conference for Innovators. Last year he was elected as one of the top 10 innovators that changed the world by the Popular Mechanics magazine. Or maybe watching TV, you've seen this commercial by Lexus called Amazing in Motion, Swarms, where these micro aerial vehicles do all sorts of weird things with the cars. So Vijay defined himself as a practitioner, and I will add to that his practice is well rooted at strong foundations. He's unique at combining theory and practice to do great research and great things. And he's also an excellent speaker, as we're about to witness. So with that, I thank Vijay for coming, and we look forward to it.
Thank you for that very kind introduction. There's a chair here, one of you. And thank you for all of you for hosting me. Yeah, you should have a chair. After that long introduction, you deserve a chair. It's really a pleasure to be here and to be able to share with you some of the work that my students and I are doing at the University of Pennsylvania. So the title of this is sort of an aerial robot swarm. It's a little provocative. I think this is what the future is, and what I'd like to do is to just tell you about some of the research problems we're tackling to make this a reality. So first, just some historical perspective. If you look at the number of UAVs worldwide, it's been growing at some a ridiculously high rate, exponential, if you will. Barely anything around the time where I got my PhD degree, and now there are tens of thousands of UAV just employed by the military. The real excitement from this comes not from the military operations, but actually from the private sector, transportation, environmental monitoring, agriculture, and also the do-it-yourself community. If you look at DIY drones, there's millions of users developing open source hardware, open source software, and so on. Just a lot of excitement in this area. And if you look at recent investments in this area, including the government, which has actually started 6 different sites where they're actually looking at UAV technologies and testing the scalability to it. As you might know, the FAA has been mandated by Congress to integrate UAVs into the national airspace by 2015. And this recent article points to 6 test sites for UAV technology. But in my mind, the real applications really come from small startup companies, Matternet, which is looking at logistics, Halo Drop, looking at emergency response, coordinating with FEMA operations, 3D robotics, which is just down the I-5 freeway in Mexico, started by Chris Anderson. Skycatch, a company that's looking at UAV platforms, and this particular example is about monitoring the construction of stadiums, the 49ers Stadium, the new 49ers Stadium in Santa Clara. A couple of spin-offs from our lab, Identified Technologies that's looking at swarms of UAVs with ground-penetrating radar that can operate in front of convoys, allowing convoys to move faster than the 2 to 3 mile per hour driving speed, which they have to do just to make sure that they can look at detect IEDs before they get blown up. So if you have UAVs sweeping the area in front, these convoys can potentially go 10 times faster. And then K-Metal Robotics, another spin-off from our lab. This particular picture shows the inspection of the interior of penstocks in dams. So if you look at these long penstocks, they're like 20 plus feet in diameter and go up at some ridiculous angle for about several hundred feet. There's really no way of inspecting the interior, and what people have to do is build up scaffolds and shut down the dam. If you have UAVs that can fly autonomously through these pipes, you can just do visual inspection and detect corrosion spots, for instance, in the liner. So these are some of the applications. The one that I'm most excited about myself is in precision farming. And this is one of our robots flying in apple orchards at Penn State in Biglerville. And I'll show you a video clip. So this is our robot you'll see flying between tree lines in orchards, and they can fly through the trees and over the trees. Pictures you can pick up from infrared imagery clearly tells you where the plants are and discriminate from the grass. With a little bit of analysis, you can actually look at chlorophyll activity in the plants and actually create 3D maps. And you might think about orchards like this and ask what's the big difference between orchards that manufacture, for example, fruits, and manufacturing facilities that manufacture widgets. Well, today, farmers really don't have any way of looking at their farm and saying where the plants are, how many fruits are there in each plant, what their projected yield is. And systems like this can just help map out the inventory, estimate the rate at which the canopy is growing, the health of plants, and also develop maps like this, which essentially tells them where their assets are. So these are some of the applications we're looking at. Another one is security and transport. So this is autonomous patrolling of a warehouse-like facility using a vehicle made by our spin-off K-Metal Robotics. So it's actually very easy to have teams of robots patrol facilities like this, and looking for simple things like moving cars or pedestrians. So if you see, for example, a white truck, at Ford Bronco, you can actually detect it and tail it. But those of you who remember the O.J. Simpson thing. So these things are easy for us. And not just overhead, but what we'd really like to do is to fly through buildings really quickly. So if you look at a lot of security type applications, the missions have to be conducted really quickly. Imagine there's an active shooter and you want to find out where the shooter is. and you have to deploy a police force really quickly. So these are real speeds our UAVs can fly, and we want to make this autonomous, as opposed to, in this case, well, some of these are autonomous, some of these, this one is autonomous, for instance, and I'll show you how we do this in a minute. But we'd like to do this really quickly and have sort of the speed of response match the speed at which security forces might respond to disasters. Another application we're interested in sort of search and rescue type missions, and so this one is these pictures taken from experiments we did in Fukushima shortly after the earthquake. This is actually in Sendai, Tohoku University, which in a collapsed building in the electrical engineering department, where we were able to basically show how autonomous UAVs, and I'll say a little bit more about this, can go through buildings like this, construct 3D maps, and provide information to first responders. So obviously everybody asks me, well, so are you working on drones? And I'd really like to say, no, these are not drones, right? And in fact, if you look at drones and what we do, there are fundamental differences. So behind every drone is a workstation like this. So there's one guy who's actually piloting these predators, and another guy who's just looking at sensor data. And these are just two of them. This is of a base station in New Mexico that's operating a Predator. And what this picture does not show you is the ground crew that's required for the Predator to take off, and another ground crew that's required for the Predator to land. And so typically for each Predator, there's maybe 10 to 20 people that are actively involved in missions. And the word autonomous doesn't even fit into this description. And in fact, if you look at what General Norton Schwartz, the person who really popularized the use of UAVs in the military, says, he takes offense at the word drones. He says they're not unmanned, they're remotely piloted. And certainly they're not dumb, right? Because there's a human that's actually controlling these. So we don't do drones either. In fact, another way our vehicles differ from all of these vehicles, I mean, these are big vehicles and fly far above the earth, and ours are really small and designed to fly in the air. So the largest vehicle we have must fit within a 30-inch doorway and comfortably, right? So that's sort of the scale that we're looking at. So there are many types of micro aerial vehicles you can imagine. So you can build small fixed-wing aircrafts, but if you're operating in environments like this and you want to move quickly with sensors that have a limited field of view, you might imagine dashing down the hallway and having to come to a sudden stop. Well, fixed-wing vehicles are not particularly good at that. Flapping-wing vehicles that try to emulate birds or insects are actually pretty good in principle. So you might imagine something like a hummingbird or something like larger birds. And here, it's really the aerodynamics of these flapping-wing vehicles that are hard to model. This unstudied flows, the phenomenon of vortex shedding is sort of hard to model. And more importantly, we have to control these, and it gets really hard to actually think about these very complex models and invert them in real time on small computational platforms that we are necessarily confined to because of the small scale and size. Having said that, there have been attempts to build small vehicles. So this one is by a company called AeroVironment, and they build these nano-air vehicles, not capable of autonomous flight. They mostly remote control these. So we're almost forced into sort of rotorcraft-like vehicles. And again, there are many variations on this. Helicopters, ducted fans that are sort of closely related to that. And in different ways of arranging these rotors. Coaxial is one of them. These are counter-rotating propellers, which are, again, good for maneuvering in indoor spaces. And then rotorcrafts with multiple rotors, and we prefer this geometry just because of the simplicity. In fact, the quadrotor with 4 rotors, I claim, is if you're a mechanical engineer and you're trying to design something really simple, something that you know has minimum number of moving parts and will least likely to fail, this is a design you quickly converge to. You take a rigid body, 4 motors, 4 propellers, and a microcontroller, and you're good to go. And that's what I'm mostly going to be talking about, particularly because simplicity is important, because we want to build lots of these and deploy these as a swarm. So the individual units have to be fairly robust and easily replaceable. So, like, you might ask, how does this relate to these a lot more expensive, shown in black in this, on top of this pyramid, the military vehicles? Well, a lot of these are very expensive, and there's few of these. And at the other end of the spectrum is all the interesting stuff that's been enabled by the consumer electronics industry. So here you're approaching unit components that sort of cost only on the order of $1 or so. And a lot of toys that people make, right? And so our real focus is taking this stuff, leveraging whatever is available, and thinking about incorporating in these vehicles the intelligence that makes them autonomous and make them agile and capable of indoor operations. So this is really where we are, and I don't even know what you would pay for something like this. But that's our focus, and so not drones and not toys, somewhere in the middle. So coming back to these quad rotors, we try to make them really small, and I'd like to argue that size does matter in these kinds of applications. And you can look at some very simple scaling laws. If you look at the characteristic length, and you look at simple quantities like mass, inertia, the amount of thrust you can generate, it's not too hard to show under some, using very simple scaling paradigms like Mach scaling or Freud scaling, that the linear acceleration that you can generate actually goes inversely with the characteristic length. So if I take the vehicle, make it half as big, well, the acceleration I can get is twice as much. And the angular acceleration actually goes even better. It's actually 4 times as much. And that's one of the reasons why we try to make them really small, so that we can quickly adapt to things that we see in the environment. So our smallest vehicles are about 8 inches in diameter, the size of my hand, and they consume about 15 watts of power, and they weigh about 75 grams. And you can see these vehicles starting from rest and quickly accelerating to a peak speed of about 2,000 degrees per second in about a quarter of a second. So these flips and double flips can be performed almost effortlessly from a computational standpoint. And they're also very good at stabilizing, and I'll say a little bit more about the question of how do you make stable vehicles and the relationship of stability to the size of the vehicle as we go through today's talk. So what I'd like to do is to outline some of the challenges. Some of these are research challenges, some of these are technology challenges, but I'm not going to try to distinguish between them. I'm just going to tell you some of the things that we struggle with as a lab. So the first set of issues have to do with thinking about the dynamics of these vehicles and autonomous control and planning for that. The second set of questions have to do with state estimation. How does the vehicle figure out where it is in a complex environment like this? The third one is a design question. When you make things smaller, they necessarily must be lighter. Well, it turns out that the power requirements don't scale quite well. So what are these constraints and how do we deal with them? And then last, how do we sort of think about large teams of robots? So I'll spend maybe 6 or 7 minutes each on each of these topics. And by the way, if there are questions, please do interrupt me, and I'd be happy to answer questions as I go along. So first, the question of control. So at a very basic level, you want to take the vehicle and you attach a coordinate system to it, and you want to think about controlling its position and orientation. 3 position variables, 3 orientation variables. And we prefer to use rotation matrices because they're free of singularities. As you know, Euler angles actually become singular. So if you're doing crazy things like flips and double flips, this is actually a lot better behaved. So in terms of controlling this, you only have 4 rotors. And so these systems are under-actuated. You have 6 degrees of freedom, but you only have 4 rotors. Fortunately, if you look at the dynamics, there's some interesting structure that you can exploit. And this structure is captured by this notion of differential flatness. So the real robot lives in the Euclidean group, which is 6-dimensional. It's a smooth manifold. But it turns out that if you were to look at 4 essential variables, which are almost flat, and those 4 variables are position and yaw. And it's almost flat because technically yaw looks like S1, but if you stretch it out, it's flat. So it turns out that any trajectory that I can realize in the real space with all the dynamics, I can actually model as a sufficiently smooth trajectory in this flat space. So every trajectory that respects the laws of physics is a sufficiently smooth trajectory in this space. So if I can describe these sufficiently smooth trajectories here, I can always go back the other way. So if I want to go from point A to point B and find trajectories that satisfy all the constraints that I have, what I need to do is find the corresponding points A and B. And I might have obstacles in this space, it doesn't matter. What I have to do is synthesize these sufficiently smooth trajectories. Now this is a problem in geometry, it's not a problem in nonlinear dynamics. And then differentiate this to get all the quantities that I need here, including the inputs. And what we do is try to find a trajectory that's sufficiently smooth, which actually is also optimal in some sense. And we try to minimize the 4th derivative of position, which is snap, so position, velocity, acceleration, jerk, and snap. And then the 2nd derivative of yaw with appropriate scaling constants. So this is a starting point for sort of an optimal control feed-forward trajectory that we can then use for control. So once we find that, we transform that into this space, and whether we do that or not, this trajectory actually respects all the constraints we're looking for. So what do these trajectories look like? So I'll show you a video clip of these trajectories in a minute. But before I do that, let me just address how we actually control along these trajectories. So again, the control, remember, is on this higher dimensional manifold. And the idea of actually realizing these trajectories is fairly simple. So here you're given this trajectory, which I've just obtained by using my optimal control approach, which again is parametrized by time and is given in terms of x and y and z as a function of time, and the yaw angle psi as a function of time. So if this were a fully actuated system with 0 constraints, how would you go about controlling it? Well, it's a 2nd order system, so the simplest way of doing it is just having a proportional plus derivative control. Oh, and you do have to have a feed-forward term, and you do have to compensate for gravity and the fact that there's a finite mass. So you might think about just naively applying a force, F, that's given by a PD control law. So the big problem is, of course, that if I take this vector and I call it T, so this vector in general is going to be in an arbitrary direction. It's not going to be aligned with the vertical axis of the quad rotor. The thrust is in this direction, the thrust that you can generate, but what you really want is this thrust. So the best thing you try and do is try to project this vector and generate this component. So you dot it with this vector, and that's the commanded direction. Of course, it won't do what you're looking for, but you also have this other degree of freedom. You're able to take this vehicle and rotate this vector so that the vector k points along t. Right? So that's the second thing you want to do. So on with the fact that you want the vector k to be pointing here, and with the fact that you want your yaw angle to be given to be exactly the same as the yaw angle that you calculated from your plan, which is psi desired, back over here. From these, you can calculate what the effective rotation needs to be, and then you compare it with the actual rotation, and then you calculate the error, and again, you have to do this on the group SO3. And then essentially you do the moral equivalent of a PD control law, except the computations are a little more complicated because you're doing it on the group. So here's the proportional term, here's the derivative term, and of course you have to, if you use Newton-Euler equations, you have to take into fact that your inertia matrix is not the identity, and you have to compensate for the nonlinear Coriolis terms, and that's the moment you want to apply. So here's the effective thrust, and here are 3 moment components, and these 2 things essentially completely specify what speeds at which you want to rotate the props. So that's the basic control law. It's a nonlinear control law, and it turns out that the basin of attraction for this is almost everywhere on SE3. So what do the trajectories look like? Well, here's where I'm planning those trajectories. Inside, I have a very tight attitude control loop that's essentially trying to figure out what the moments are. An outer loop essentially tells the robot what thrust to apply, which is this force F. And so this innermost loop operates at about 1,000 hertz. The one outside is about 100 hertz. And then the trajectory planning loop operates around 10 hertz, roughly speaking. Now, to implement this, I do most of these computations that need this very, very fast loop on board. And this requires attitude estimation and attitude control. But things that don't have this very, very high bandwidth requirement, I can do off-board. And in particular, if I design this properly so that the inner loop has a very large basin of attraction, the outer loop actually can be done off-board. And oftentimes I can use external sensors. In this particular case, I'll show you how we use motion capture cameras to estimate the position and velocity, and how we can do the trajectory planning off-board on a laptop, similar to the one I'm using. Again, I want to emphasize the fact that this is quite important, the fact that you have a very large basin of attraction. In fact, here's Sir Daniel Mellinger, the guy who designed the control algorithm. If you look at the properties of the control algorithm and you look at the basin of attraction, this basically tells you that it'll converge to whatever attitude you want to go to from everywhere except a position where the rotation and the desired rotation are diametrically opposite. So if you want to get to this pole of SO3 and you start at this pole, that's the only point where it doesn't work. The other thing you'll notice is that if you look at the allowable angular velocity errors, this quantity, again, depends on how R desired and R are different. But you'll also notice at the bottom, you have the smallest eigenvalue of the inertia tensor. So what this is telling you is that the smaller you make the inertia, the smaller this eigenvalue and larger this right-hand side, which means the larger the allowable errors in velocity. So this is essentially telling you make it really, really small, and the intuitive idea is that you can recover more quickly from perturbations, which is certainly true, and that's one of the, again, another motivation for us to do things that are really, really small. So here's the minimum snap trajectory, now putting everything together. Starting from this position, going to that position through an intermediate point. And again, you have to remember that this trajectory is planned only in position and yaw space. So in other words, when we do this optimal control problem, we really don't pull in all the additional angles, all the dynamics. This is purely a problem in geometry in a four-dimensional space that's roughly Euclidean. So this is a trivial problem to solve. And we can do it as fast as we really want to, but it turns out that 10 to 20 hertz is enough. So once you can do that, you can also now get it to go around obstacles or through obstacles in this case. So keep in mind, again, the motion capture cameras here are telling the robot where it is at 100 times a second. It also knows where the obstacles are 100 times a second. So if you specify the environment completely, even if the environment is changing, it's a time-varying environment, for the robot to calculate trajectories that are consistent with constraints in this time-varying environment is quite easy. And executing these trajectories, like I said before, if you have a good controller, you're going to execute them. And we can do some fairly high-precision maneuvers at high speeds. Of course, here the robot is actually predicting how the hoop is going to fall, and it actually accounts for that when it factors in the time-varying constraint. So this is roughly how we do our dynamic modeling, our control and planning. There's a few more twists to it, like adaptive control loops to account for all the uncertainties that we have. But I'm going to skip that and move on to my next topic, unless there are some short questions, and I'm happy to answer that to just punctuate the talk before I go forward.
So do you ever come to any limits of computation when you're doing this dynamic?
No. If you assume that the environment is known, and this is roughly about 2 years ago, when we were doing everything on an ARM8 processor and a laptop like this, there are no problems. Now we have even bigger processors. The big challenge will come when I talk about state estimation, where I don't know what the environment looks like, and I don't have these motion capture cameras. The other thing you might ask is, where's the computation done? And as I said before, this is really more of like a cloud computing type setup, where there's somebody that's talking to all the cameras and telling the robot where it is as frequently as the robot needs to know.
So that was my second question. So you are relying on infrastructure, cameras to do localization.
Yeah.
Do you have a version where you actually do it on the device itself?
Next part. Any other questions? Yes?
Is the 2000 degree a second angular rate, is that required to be stable if we're doing like 200 degrees a second?
So,
You said the small robots can do 2000 degrees per second.
yeah, I mean, we just wanted to see how quickly we could flip, so you have to accelerate really
So you
quickly.
don't need it.
And plus our lab is only 20 feet high, so you have to do those rates. But it really has to do with how good your gyros are and how tight your control and estimation loops are. So let me move on and talk about the next problem. So apropos this question, what happens if you go into an unstructured environment? I want to do first response. I can't expect people to set up motion capture cameras before I go in there, right? So this was our first attempt about 3 years ago, where we said, well, let's try to build in sensors on board that will allow us to do the kind of estimation that we need to travel at high speeds through cluttered environments. And our first attempt relied largely on a laser scanner. This is made by a company called Hokuyu, which essentially is a planar scanner. It has a 270-degree field of view, and it goes out to about 20 to 30 meters. And essentially what it does is it allows us to build a depth map. So if I could shoot out a laser beam here, I can map everything in this plane to the end of that wall. That gives me some idea of where features are in the environment. This Xbox sensor is essentially, well, you know what an Xbox sensor does. It's good to about 3 to 5 meters out and field of view about 40 degrees. So that gives you sort of a 3D depth cloud, and it's particularly useful for seeing things that are out of the plane. So how can you use a sensor like this and actually estimate where you are in the environment? So to illustrate that, let me start with a cartoon. And again, the key thing is I want to estimate R and R dot, the position and velocity, and then the orientation and the angular velocity. So the cartoon has the robot here and 3 pillars. And I don't know where the pillars are, so the robot doesn't know x1, y1, x2, y2, etc., etc. It doesn't know where it is either. But it does have access to this laser. And so if I use the laser, I can determine what these distances d1, d2, d3 are. So that doesn't help a whole lot. If I knew where the pillars were, I could triangulate and determine where the robot is, but I don't know where the pillars are. But the robot can move, and on board we have an IMU and gyros that allow you to estimate the new positions relative to the old position as it moves. So these are noisy estimates, but when I get to this new position, again, I have 3 more measurements of where the pillars are. And now I'm on with 6 pieces of information, 3 scalar quantities, another 3 scalar quantities, and 2 vector quantities. I'm sorry, 1 vector quantity, which is 2 variables. And the question is, can I write down enough equations to figure out where the locations of the pillars are and how much this delta x is? And it turns out you can. So this is basic trigonometry. You can do this. But what we have to do is solve these equations in a filtering framework, and you have to do it really quickly, 100 times a second. We're replacing the motion capture cameras with this algorithm. And this idea is called simultaneous localization and mapping. I'm not only estimating where the robot is, which is localization, but I'm also mapping where the pillars are. And of course, in robotics, we have this nice acronym, SLAM, and again, we have to run this on board at 100 times, roughly 100 times a second. So this is actually doable if you make some assumptions about the world. In particular, you assume that you're living in a world that is roughly 2.5D. So most human-made buildings satisfy that assumption, unless you go into a Frank Gehry building, those assumptions are off. But here's an example in a non-Frank Gehry building. So the robot starts out outside, and it's able to then triangulate features in the environment. And what you see here is the map that it's building in real time. This is sped up 4 times. The operator that's sitting outside the building, and this is work by Frank Shen and Nathan Michael, actually sees this map and is able to click his way to new points. So here Frank clicks on this point, the robot plans its trajectory, and as it goes there, it uncovers more information about the environment. And again, the blue colors are the ground floor. As the colors get hotter and hotter, the robot's going higher and higher. So we're able now to not only estimate positions of obstacles in the environment, but also we allow the robot then to estimate where it is relative to the features. And this operates quite seamlessly. We don't have a global coordinate system, but yet we have a coordinate system that's attached to this map. And the operator can choose to see what the robot is seeing, but in reality, this is the kind of information that helps him the most. So he's just clicking his way through different rooms, and without entering a building like this, and you can imagine for security applications, law enforcement, and so on, you can have a robot go into a building and just figure out where the walls are, where the windows are, and if there are bad guys hiding somewhere, you can actually detect those quite easily using this, with some modest assumptions on the environment. So this solution was about 3 years ago, and the thing I wanted to point out is that something like this ends up being about just the size of the doorway, a little smaller than that. But it also ends up being about 2 kilos and consumes about 400 to 500 watts of power. And the reason for that is you're carrying all this stuff on board. When you carry lots of stuff, you have to make the propellers bigger, which means you have to have the motors, they have to be bigger, which means you have to have bigger batteries, and that in turn drives up the weight, so the batteries have to be even bigger, and so the scaling problem takes you in the wrong direction. And so to think about something like this requiring 500 watts, nearly half a kilowatt, I mean, that's really not something that as engineers we want to work with. And plus, as I told you earlier, you make this bigger with larger inertia, and you're going to lose some of that agility. So, and this is really the main difficulty we deal with. You want to make things smaller, but you run into the scaling problem the minute you say you're not allowed to have motion capture cameras overhead. So, yeah, sure.
Have you tried to build the same map using multiple robots? For example, every robot should have different.
That's the punchline. We come at the end. So just hold on. Yes, I mean that's one of the things we'd like to do. But again, going back to your point, I mean, every robot has to have roughly the same capabilities. So I guess one way of answering your question is, well, if I have lots of these very, very heavy robots, I could easily get them to do this in parallel and try to register these maps on the fly. Yes.
How much of that weight, though, is due to the case that the applications for which the Kinect and the laser scanner were designed were not weight and power sensitive, and how much is fundamental to those devices?
So I'd like to come back to this discussion. So I would argue that any kind of range sensing, which is sort of active, involves using a laser or something like that and shooting out beams, and that ends up being a power-hungry and, more importantly, weight-hungry operation. As I'll point out shortly, every time you add weight, you also add more power because I got to take this and sort of have it fly in air. That takes me in the wrong direction.
What about a bat?
Sorry?
A bat, little bat, flies and it's not very heavy.
So you can do echolocating with sonars, certainly that's one way of doing it. But again, you have to have active sonars doing the pinging.
It could be small.
Well, remember, what I want to do is build a three-dimensional map, and for that, you have to have lots of these. And so you can ask if a bat actually ever tries to build a map or not. I don't know if it does. But a bat is just trying to navigate through a complex environment and not worry as much about where it is specifically in the environment. So I think these kind of requirements are very unique to robots. So going back to the question of power and weight, so this is a plot of many lithium polymer batteries that our collaborators at the Army Research Laboratory tested along with one of my students. And on this axis you see specific energy, and this axis you see specific power, so watts per unit kilo, watt hours per unit kilo. And you notice that, and again, these are commercially available lithium polymer batteries. We don't try to make our own batteries. So you'll sort of notice this sort of narrow band. And so the bad news is if you want to be operating for long periods of time, you're just not going to find them, right? You're not going to find those batteries. So if you look at the batteries we use, they all fall in this band. In fact, our quadrotors consume roughly 200 watts per kilo. Now, you can reduce this if you put a lot more work into designing flying robots. But if you want to build really simple robots and you want to make lots and lots of them, you're basically stuck with this. I mean, hovering is not a very efficient way of flying. And our robots hover just by virtue of their design. So how does this compare to humans? Well, this is a picture of adipose tissue, fat. And you can see this is off scale. This is like 10,000 and this is about 500. So and all of us have enough of this to look down on flying robots and say, hey, we can do better. Right? On this axis too, we actually do much better than robots. So most of us don't consume a lot of power. But if I single out the two athletes, I think that do. One is Usain Bolt, 10-second dash, he consumes about 20 watts per kilo. So that's, and he's one of the most inefficient people in the sense that, why would anybody want to run a 10-meter dash unless there's a gold medal waiting at the end? And we are not enticed in similar ways. But even if we were trying to be as inefficient as Usain Bolt, the maximum we would be is 10 watts per kilo. This is Lance Armstrong, 20-minute stretches. And again, with steroids or without steroids, you're still pumping the same amount of energy. So this is an objective study, not tainted by steroids. So 6 watts per kilo, and our robots are just far too inefficient. So we cannot play the sort of the long endurance game, and we're going to be stuck with this unless there's like a dramatic improvement in battery technology, which I don't think is happening in the next 5 years or so. At least if you look at research on lithium-based chemistries. So what's our solution? Well, solution is quite simple: lose weight. Right? That's the one thing we have under control. So somehow they make things lighter. So over the last couple of years, we've started converging on what I call the flying smartphone solution. So the flying smartphone solution uses roughly the same kind of hardware you find in a smartphone, right? In fact, if you look at the S4 Galaxy, the new Samsung phones, it's actually the computation power is more than this, and the RAM is more than this. But you look at your standard iPhone, 2 cameras, one front-facing, one back-facing, and a whole bunch of sensors that you find on an iPhone. So it's something like this. There's no laser, but you have 2 cameras, and those cameras actually can be made lighter if you spend some time on it. But this is something which we built with off-the-shelf a couple of years ago. So down to 740 grams, consuming about 1/4 the power of the bulkier robot. So the problem with this is that now the SLAM problem, or sometimes called the structure for motion problem, gets a lot harder. So I want to show you. So if you look at this as a vision problem, the problem ends up being terribly nonlinear and terribly hard to solve, especially in real time with these kinds of constraints. So what we try and do is sort of break this up. And by the way, this is what the robot is looking at. So if you look at this picture, this is our lab, and you can see the features that the robot is detecting using a standard feature detector and a standard tracker. And this is a modestly cluttered environment. There are no pillars, but those pillars are essentially replaced by features that it detects. And in fact, you'll see a lot of features on this whiteboard. It turns out if you have equations, those curved, the sigmas and the epsilons actually work really nicely. But anyway, it detects those features, and here it is trying to map those features and extract its pose. One of them is a true pose as measured by the bicon. The other is one that's estimated by this algorithm. So the key to this, if you want to run this really quickly, is you decouple the problem into several sub-problems. Each one of them is linear in flavor. So what are the sub-problems? Well, in this case, you have to estimate rotation, you have to estimate translation, and you have to estimate where the features are. So if you assume 2 of them, and you try to solve for the third thing, so for example, if I tell you what the rotation is, and I tell you where the position is, and I ask it to estimate the features, well, that's easy to do from just the cameras. Likewise, if I tell you where the features are, and I tell you what the rotation is, to estimate the position is actually easy. That's a linear problem. So each of these problems is solved, and there are interleaving processes that solve this problem in a way that you can actually do it on a fairly simple processor. And this is done so that the robot has a 100 hertz estimate of where it is relative to all the features it sees. Not great for building a map, but good enough for doing estimation. And so let me show you some video clips that illustrate this. So on the top left, you see our robot flying down a hallway at about 4 meters per second. This is about twice walking speed. Again, no external motion capture cameras. This is true speed. This one is sped up outdoors, and it's in the presence of foliage, and you can see that in spite of the downdraft from the rotors and the fact that the leaves are all blowing, it finds enough features that it's able to triangulate its position relative to the features. This is much of the same thing, again, in real time, without speeding up, but in more three-dimensional environments. And this is outdoors, and this is sped up. This is going relatively slowly. It's about 8 times sped up. And you can see the kind of maps the robot is building. Not the same kind of maps that you saw earlier with the laser, but if I had access to off-board computing, then I could think about creating dense maps and reconstructions that would allow us to build a nice user interface that allowed the user to sort of plan trajectories and so on. The main goal here is actually to try to get all of this state estimation stuff to run on board with lightweight sensors. And again, we're sort of converging to using just cameras and onboard IMUs and gyros, the same kind of hardware you can find on a smartphone, and something we know that the price-performance ratio will continue to drop, because these are the things that everybody wants. So that's how we do our state estimation. Any questions before I move to the last? Yes?
So each of these problems, you solve them iteratively? So because
Yeah.
I see. So
So
whatever
the processes are interleaved.
and do you have any guarantees on
So-
this thing is going to go?
So individual processes of guarantees, in fact, they're all linear or convex, so we have those.
Yeah, but once I...
No, and it's actually hard to do. These are nonlinear problems, and most people try to build these extended common filter type representations. But if you do that, the state vector that you have grows with the number of features.
Right.
So if you look at any of these experiments, the robot's tracking about 1,000 features. Well, I have to think about covariance matrix, inverting covariance matrices that are roughly 1,000 times 2, which is 2,000 by 2,000, plus some other variables. So you can do that, but there's no guarantee that will work. And the way we've designed this, we have all the failure modes that we've seen. Actually, we're able to accommodate them in this kind of framework.
Okay, can I ask a question? So you haven't explored the possibility of just a touch sensor that it bumps into a wall. I mean, if I was a terrorist and I don't want these things to come in, I just put a little chicken wire up.
And
that's it.
in fact, so one thing that this doesn't do is actually work well with glass windows and glass panes in general. And the only way we can detect those,
in the previous you had some boundary
yeah,
around
it bumps into it and it knows there's something there which it's not consistent with the map. But to map like a wall by just touching it, it would take forever. So you'd have to make some assumptions. Well, I banged into this fence, and by the fences you can detect, so that's not the problem. But if it was a glass wall, you'd have to have some heuristic that says, here's a glass wall, which means it probably extends up this way or this way, and then try to work around that.
How are these videos captured? Do you have a human walking behind?
This one is the hardest one, because if you're standing there and looking at something that's flying at 4 meters per second, that's hard. But yeah, there's a human capturing all of these. Yeah. Well, this is directly off the laptop screen, and this is also off the laptop screen. But these are actually captured by somebody following it. A question at the back.
You have 2 cameras, but it doesn't look like you're using stereo vision or visual odometry, but you're using the one camera to track features?
So the second camera you need to extract scale. So actually you can show that if you take a single camera and the IMU and you write down the filtering equations, well, you can show that the system is not observable. So if you take one eye and you don't move, and you look at accelerations that you get from your head, you cannot recover your absolute position, neither can you recover yaw. You might be able to recover the gravity vector, which tells you roll and pitch, and you might be able to look down at the floor and recover z at most. But the problem is ill-posed. So you really need that second camera. And in order to speed things up, you operate the second camera at 1 hertz. While the first camera, the primary camera, is operating as fast as we can get it to work. How much time do I have?
10 minutes.
Okay. All right, so let me move on and say a little bit about how we think about swarms of aerial robots. So first, I know some of you are familiar with this literature, but let me give you some of the challenges at a high level. So if you think about mathematical modeling, it's useful to think about models for small groups versus slightly larger groups. So in small groups, you might think about architectures where all the data is centralized, all the information is fused centrally, and there's a central machine that computes all the control actions. Where individuals are labeled, right? If you get to larger groups, this becomes hard. You can still have individuals labeled, but to do things in a centralized way can oftentimes become hard. So people generally try to work with decentralized algorithms where control actions are computed independently. And of course, if you get to really large groups, you can't assume that things are centralized. And the labeling question also becomes problematic. So just to know who is robot number 1, who's robot number 2, or ant number 3, and so on and so forth becomes hard. So you want to go towards a paradigm where things are anonymized. So notion of anonymity, in fact, you don't even want to know how many individuals are there. So ultimately, if you can shoot to this kind of a framework, your algorithms are sort of guaranteed to be robust to individuals breaking, robust to not having the right group size, and robust to not having the computational resources on individual agents. So you can have very simple individuals collaborate to do large, very complex tasks. So that's the whole idea. So we want to drift towards that. So let me just give you some sense of where the complexity lies by simply considering a very, very simple problem. So this simple problem is a problem of planning. So imagine I had 3 robots starting at S1, S2, and S3. And I told them that they have to go to goal positions. And I don't care who goes to which goal position. So the first problem you have to solve is determining who goes where. Right? So I've given this label 1, 2, and 3, which is essentially the assignment problem. I've told which robot needs to go to what goal, and there's basically an assignment matrix with zeros and ones that designates this. The second thing I have to do is plan trajectories. And these trajectories have to be planned in the joint state space, and you can see that the size of this vector goes with the number of robots. And these are continuous trajectories, and hopefully I want safety, which basically says, well, you know, this has this extent, and that has that extent. I don't want these two to come too close to each other. And I want some optimality. Again, some optimal control, some cost function that I try to minimize. So this is really the problem I want to solve, and the key questions are who goes where and how do they go? So where does the complexity come in? And by the way, there are obstacles too, right, which I haven't modeled here. So if you have n robots and m obstacles, what are the challenges? Well, as I said earlier, the dimensionality of the space grows linearly with n. So this is order n. The potential interactions with neighbors goes as n squared. For every robot, you have to look at every other neighbor, and that's n choose 2. With obstacles, if there are m obstacles, then there's n times m interactions. So this goes as order mn plus n squared. And then finally, the assignment problem is an n factorial problem. So all of these 3 things have to be done simultaneously. So if you take standard, without using supercomputers, off-the-shelf laptops and things that you could buy in an Apple store, my preference, you go to, so this is an example of what you can do. So 3 robots, this is Quentin Lindsay's work, 3 robots assembling In this case, truss-like elements to build prescribed structures. So all of this planning can be done in a centralized way. The robots collectively as a team decide who goes where, picks up what part, and how to assemble it. So the assembling problem, by the way, is trivialized because each of these truss elements has a magnetic fastener at the end, so they just snap into place. So it's a little simpler than Lego, but the problem of building something is similar to the problem of building Lego structures. So all of this done automatically from just a blueprint of what the structure needs to look like. And this planning you can do centrally with 3 robots in a modestly cluttered environment. If you take laptop-like infrastructure, computing resources, you can probably push this to 3 to 5 to maybe 8 if you're lucky. But that's the limitation. So how do you overcome that? And I just want to give you sort of 3 different ideas. So one very classical idea is that, well, you don't allow them to go in independent directions. You try to collect them as a team. So in the controls literature, this is often called formation control, but the central idea is every robot monitors its separation with respect to its neighbors, and they all try to maintain desired separation distances. And what you have to do is just plan the motions for one of these guys. So here's this guy now planning in this flat space, and all these others are trying to maintain these distances. Now in reality, it doesn't have to be this guy, it could be anyone else. In fact, they could even elect their leader, or it could even be some virtual leader that's specified. But the idea is that you have this network of robots where the network is established by physical connections, and where the physical connections have to do with separations in position and also in terms of the orientation angle. And there's a bunch of literature in this area. These are called leader-follower networks. I want to show you how this looks like. And David Pope did a NOVA segment in our lab, and this is David illustrating this idea. This is, by the way, Katie Powers' work. So these are leader-follower networks. Here, David is the leader. He just grabbed one of our robots, and all the other robots think, well, you know, it's flying this way. We're going to follow it. And it's a very simple idea. But all of a sudden, you've taken the complexity of the system and reduced it to a point where you have to just worry about one team member, and everybody else sort of falls into place. And so if David does a good job and makes sure that the team actually will not collide if he walks a certain way, everyone else can sort of fall into line, and you can solve this. So this is one way of scaling up. It's a pretty boring way of scaling up because all of these guys are doing exactly the same thing. They're maintaining this virtual structure. Another thing you could try and do is this notion of anonymity that I alluded to earlier. This is Matt Turpin's work. And this just illustrates the point that these robots, when they enter the team members look at their neighbors and figure out, hey, someone new has come in, and they automatically space themselves out. So the formalism that we try to develop is necessarily sort of this anonymous. It's agnostic to how many team members there are and who the team members are. So this is sort of the second idea. So to tell you why this is important, let me go back to this previous idea that I mentioned earlier, where the complexity grows pretty dramatically. So if you concurrently assign goals and figure out the trajectories, it turns out that that problem, surprisingly, is simpler than first assigning goals and then planning trajectories. Right? So to show that, let me give you a very, very simple result. And the result says that if I were to make sure that the starting and goal positions are sufficiently far away, R is the radius, so I'm just going to space things out. Just saying that these things don't have to be too close to each other. So here's a very simple idea you can prove. You can ask what these different cost functions are. So if a robot were to start here, go to this goal, start here, go to that goal, start here, go to this goal. And if I know all of these distances or cost functions, here's a very simple idea. I can treat this as a gigantic optimization problem where I look at assignments and trajectories that minimize some big cost function over all the assignments and all the trajectories. if I can solve that, it turns out that collision avoidance is automatically guaranteed. So this is the n factorial problem, the assignment, and this is the planning problem, which is hard because you want to worry about collisions and safety. It turns out if you forget about collisions, this assignment problem actually guarantees that the trajectories will be safe. And that's a property of the Euclidean geometry, and just the idea that if you actually were to find optimal trajectories that satisfy this cost function, that minimize this cost function, the resulting trajectories will never intersect. So this idea you can take and apply to more complex situations, and you'll see now, and this turns out it's only an order n cubed algorithm, which allows you to scale to large n as well. And so this is now, again, Matt Turpin's work, where you see these robots, they're asked to follow a particular trajectory, and they're asked to maintain a certain shape. And the shape, as you'll see in this video, changes from a rectangle to a circle, flattened to a straight line, and then back again into a circle. At no point are individual robots told where to be in the shape or how to fly. The description is given to the entire team, and every robot sort of solves this problem and tries to figure out where it needs to be in the slot. And this is an even more complicated problem with 20 robots, where now we're telling the robot to adapt its shape to an environment. So here it's just a 3D formation flattening out into a 2D formation. But now in a few minutes you'll see it trying to go through a narrow constriction. Again, individual robots are not told where to go in this formation. All they're told to do is to make sure that they maintain these shapes, and they're solving concurrently this simultaneous assignment and trajectory planning problem. So this is one way to sort of overcome the computational limitations and the scaling with large n. The real thing we want to do is apply these methods to search and rescue. So this is going back to the experiments we did in Sendai, where we had one of our robots with a ground robot made by Tohoku University. And again, our robot is hitching a ride on this platform, mainly because it's lazy. It's programmed to be lazy. It saves power whenever possible. But when the team gets stuck, like in this collapsed doorway, the ground robot releases our aerial robot, goes in, it starts building its map, and then so concurrently they can sort of, the question that was asked, they can each construct their maps and stitch these maps together and build a 3D map. So in this case, we're able to go into this room, autonomously look beyond that bookcase, which would have been impossible to do with a ground robot, and a human would have needed a ladder, which could have been dangerous in this particular setting. To cut a long story short, this was a 2.5-hour experiment where we built a map of the 7th floor, this is the 8th floor, and that's the 9th floor, collaboratively between one ground robot and one aerial robot. So we'd like to do this, but now we want to do it not in 2.5 hours, we want to do it in 2.5 minutes, if not 2.5 seconds. And so if we can somehow take that big platform that I showed you and make it really small, and we're able to solve these planning and assignment problems and the mapping problems concurrently, we can just get them to fly through this environment and then stitch the map when they come out at the other end. And if you send 100 in, maybe 20 die, it doesn't matter. But as long as you get the data when they come out, you'll be able to stitch the pieces together and get a complete map. So that's really what we're going towards. I don't have an audio jack here, but I wanted to show you this this video that Jorge alluded to. This is, again, my former students who created this commercial with Lexus. And this is really showing you, this is a great video. So if you Google Lexus swarms, you'll get this video. So I'll let you watch this with audio. But these are the robots that they've created, and the whole, some of this is science fiction, some of this is sort of computer graphics. This is clearly computer graphics. But it's a great video that really shows that the sort of the power of swarms technology. And I use this to make the point that The swarm is coming. So, you know, everything about this poster is true. I think the size, so this is, by the way, it's a really bad movie. You shouldn't watch it. So I've actually read the book when I was a teenager. It's about killer bees coming after humans. But this poster is true. Its size is immeasurable, its power is limitless, and its enemy is man or humans. Because we really, if we had applications for it, we wouldn't stand in the way of this technology. So I think this is inevitable in some sense. So let me thank you with a yoga pose from David Koch. Thank you very much. I think I overshot my
No, it's
my
fine.
time limits,
It's
but
fine.
I'm happy to stay back if somebody has questions.
So let's take two questions, short questions to end the this particular session. We'll take the questions from people who have not met Vijay as yet, or who will not be meeting Vijay soon. So, two questions. All right, go ahead.
What are the sensors of the small ones?
Okay, so this, so good question. I just, they don't, the only sensors they have are onboard inertial sensors and radios. So in effect, they sense the neighbors by talking to each other. And they know where the neighbors are through the camera system in this particular set of experiments, yes.
I'll make an exception for Tom. Go ahead.
Oh, okay. A parrot or a pigeon, pigeons when they walk, they do this.
Yeah.
And so they get a view from here, they get a view from here.
Yeah.
And from that can construct a 3D view with one eyeball on this side
Yeah.
and one eyeball on that side.
Yeah.
So that's a way around requiring two cameras to get a 3D view.
Absolutely, but when you...
Similar or possible in this frame.
It's absolutely possible, but again, you have to ask, if you want to make something with low complexity, do you want a nodding head or not? And then you can say, well, I don't want to do a nodding head, but I can move. Exactly. So the real problem comes in is when I take off. When I take off, initially I know nothing because I don't have these unabsorbable degrees of freedom. So once I take steps, I can actually figure out where I am. Mm. But remember, we're dealing with cameras that are not as powerful as the cameras that you and I have. So if I take off in the middle of a room and I don't see any features, it's going to be a while before I actually know what is going on. So I think there are some of these reasons where you want to take off at ground level. At the ground level, you can see some features and you can triangulate and build an initial estimate, after which you can sort of at least survive while you go.